Okay, thank you, Romain. So my screen is visible. It's right. You can hear me well.
Yes, everything is going well so far.
Okay, so just send me a message in case it's not working as expected.
We will.
Okay, so in our case with Olivier, my colleague from with whom I'm working on the MB412, it will be much less theory and much more experimental data. And it will concern what we do on indium phosphide substrate, and especially quantum dash on indium phosphide and some data we obtain from laser epitaxy and amplifiers. Okay, very quickly, at 35 Lab, we have multiple epitaxy reactors. Two MB multi-wafer reactors, MB49 for antimonides and our MB412 dedicated to phosphoric-based material, gallium indium arsenide phosphide. And we also have 3 MOCVD reactors. And at least 2 of them have the competition tool. And I have to say already that EasyCurve is much more sensitive as compared to the competition of Reber. So in our case, we are growing many different kind of devices, lasers, DFB lasers, EMLs, photodiodes, optical amplifiers, and we are systematically using EasyCurve on all the type of structures we are growing. Of course, it's working only mostly on 1x3, 1x4, and 1x2 inches substrates, holders. And if one day it was possible to transform it to be used on 3x2 inches or multiple multi-wafer, it will be really great, at least at the production level. So this is our MB412. You can see here the light source from the EasyCurve system. And we have on our tool aluminum, gallium, indium as solid sources. And it's a gas source MB system. So we're using arsenic and phosphorus for 5-element sources. We also have silicon and beryllium for dopants, solid, and also CBr4. So our system is equipped with many classical and state-of-the-art characterization tools. So KSA Bandit for temperature measurements, a 20 keV read system from STEB, and of course the EasyCurve. And here in the middle on the table, I put the sensitivity from publication from Alexandre Arnoux. And as I said just before, we are really much more sensitive to every kind of modification we do during the growth as compared to the latex tool, I would say. I will explain where the difference are later on. So we are using EasyCurve in 2 ways. First, for real-time monitoring, and also for follow-up analysis. So when we want to do some real-time monitoring, it's as Alexandre already mentioned, it's for the lattice matching of gallium indium arsenide on indium phosphide, but also by changing temperature of our gallium and indium cells. And we are also working on gallium indium arsenide phosphide. And mostly when we modify and we want to target the lattice matching, this time we're using the arsenic and phosphorus baratron pressure transducer from the attached to the HTA 440 gas injector. And also when something unexpected happened during growth, outliers, I would say, this is something we can see very, very quickly and directly. And another application that we would like to use more efficiently, but we have not been able to do for now, is to check any drift of gallium, indium, or any other cell during the growth of very thick quaternary alloys. So for example, in some of our structures, we have 4 to 5 micron thick gallium indium arsenide phosphide, and we can have some drift on the free element cells. The second application for us is after growth. We are using it to check the run-to-run reproducibility. That's very important for us because we have to provide to our customers, external and internal customers, different kind of devices such lasers, as I said, SOA, and it's very important for them to have identical epi wafers. And I would say that since the sensitivity of EasyCurve is so high, is so good, we can see if there is any problems or drift or anything during the growth. Recently, we have also used EasyCurve to make some studies about the quantum dash and laser barrier strain to adjust the growth condition for indium arsenides on indium phosphide, the quantum dash lasers, but also how to adjust very precisely how to compensate I would say the strain of the quantum wire by adjusting the strain of the barriers. And again, we can see if there was any outliers during the growth after growth. Okay, I would have to say that mostly it's mistake in recipe on my side. Hopefully, Olivier is correcting me quite a lot on that topic. Okay, so let's have a look first to what we obtained from DFB laser growth. So here on the left, you have DFB laser growth that we have done using EasyCurve. So as you can see here, we are pretty happy with the sensitivity because we are growing at quite high growth rate, more than 1 micron per hour. And the quantum wire duration and the barrier duration is quite small, between 30 and 40 seconds each. And even at 20 RPM rotation speed, we are able to see the quantum wire here on the right graph, and the barrier here on just below. And all the single quantum wires are clearly visible using EasyCurve. Okay. And from that, we are able to see that, of course, the gallium indium arsenide phosphide quantum wire is compressively strained, at least at gross temperature, and but also at ambient temperature. But also the gallium indium arsenide quaternary alloy from the barrier is also at gross temperature lattice match to indium phosphide. Okay, and here we can see that the strain from each of the quantum wire is identical, and that's the same for the barrier. And if you look on the right, the red curve, that's quite interesting because here what we did was to, we modified only by 500 ppm change in arsenic pressure into the barrier, and we see here that even it is very small change in the phosphor and arsenic over phosphorus ratio in the barrier has changed the way the barrier was grown. Okay, and here we see that there is even some kind of drift from the first quantum wire to the last quantum wire. But now, if you look at the blue curve and the black curve, we can see that the reproducibility from one run to the other is really good. Okay, and during the two wafers, 1098 and 1112, we have grown about 15 wafers without any drift or anything. Okay, but any change in the recipe is really visible using EasyCurve. Here also I wanted to show that even if the wafer is patterned, for example, we have made some on top of a electro absorption modulator, we have which has been processed by the process team here at 35 Lab. We are still able to see the growth of the DFB laser, butt joint laser on the edge of the EAM. So, of course, considering that the surface is not smooth and there are many different kind of patterns on top, the signal is not as sharp as on a bare substrate, but still we can observe the 6 quantum wells here on the red curve. Okay, so that's still interesting even on pattern substrate. Another application for us is, as I said before, amplifiers. So here at 35Lab, we are growing ultra-wideband amplifiers for which the quantum well is much more thick than the barrier, and for which the compressive strain is very high. Why it's high? Because we have to reach the L bands in order to have a very large band amplifier. And in that case, we are adding a lot of the arsenic over phosphorus ratio is very high. Okay, and in order for that for devices to be let's say functional, we need to compensate quite a lot the strain from the quantum well by the tensile strain of the barrier. And here, that's what we did when we have grown this SOA with pretty thick quantum wells, pretty thin barriers, but with a very let's say quite high tensile strain. And from that, we've been able to grow both O band and C band SOA. Thanks to the study, we could let's say find from the easy curve. But let's now focus a little bit, and maybe not that much, but still it's quite interesting considering the capability of easy curve on what we do on quantum dash lasers. So here at 35Lab, we are working mainly on the Nokia side, at least on the Bell Labs side, on indium phosphide, and we have to grow devices between 1.3 and let's say between O band and L band, and O band and C band are our main focus. And what we did over the last few months was to develop a quantum dash on indium phosphide process, which allowed us to obtain lasers at 1.3 and at both 1.3 and 1.5 micron on indium phosphide. It was quite interesting for us because all the processes we have developed here was focusing on indium phosphide. And if we had to grow indium arsenide on gallium arsenide quantum dots, we would have to redevelop a lot of process here. So it was really nice for us to have this capability of having quantum dash lasers at 1.3 and 1.5 micron on indium phosphide. And okay, I don't want to go too much into detail on that, but growing 1.3 micron lasers based on quantum dash on indium phosphide is not that easy, because the strain between indium arsenide and indium phosphide is much lower as compared to indium arsenide and gallium arsenide. But still, this is something we've been able to do. And as you can see here, by using easy curve, we have been able to control quite accurately the way we have grown this quantum dash lasers from 1.25 micron up to 1.61 micron. And I don't think that's something that is that easy. And I think that's really let's say that easy curve helped us a lot. And as you can see here on these slides, on the right especially, is the easy curve measurement of different kind of quantum dash lasers, active layer at least, that we have grown at pretty high growth rate, 0.8 micron per hour, and we were only rotating at 20 RPM at that time. And with indium arsenide quantum dash with varying growth duration from 3 seconds to 7 seconds. And even at 3 seconds, this is the blue curve here, we are able to see the strain brought by the indium arsenide quantum dash. Of course, the longer the quantum dash, the better it's, the easier it's easy to see the curvature of the substrate, but still here, when we tried to adjust the growth conditions for such lasers, so O-band lasers, it's if I remember well, between 3.5 to 4 seconds. So here we have been clearly able to see each of the quantum dash we have grown between the gallium indium arsenide quaternary alloy barrier. Okay, and here for the 1.5 micron laser, that's the same. Okay, but of course it's even easier. So I would say that we were pretty impressed with Olivier by the capability and the sensitivity of such of the tool developed by Alexandre. And now, if we compare what people were using the LaTeX tool by MOCVD, they don't see that. For them, it's impossible. They just observe some kind of mean, let's say, strain from the first quantum well to the last quantum well. I'm not even talking about quantum dot or quantum dash here, but they see a mean strain from the first to the last, and not all each layer from during the epitaxy. And all this is, of course, related to the X-ray diffraction we did, and we observed that for this, you can see here the 4.2 seconds for the O-band laser and the 7.6 seconds for the C-band laser. And I would say that in our case, we have been able then to adjust very accurately the way we have grown, especially the barrier, in order to control the full stack of the quantum dash lasers. And of course, all these experiments I showed you here, they have been done on 1x2 inches and 1x3 inches wafers. Here, we have used all we've learned from these studies and experiments on 3x2 inches substrate holders, and we have obtained extremely good uniformity. It's not that easy to see, but the standard deviation is 0.4 nanometers on the wavelengths. The intensity is also extremely good, even better than what we obtain on quantum well lasers, 3%, let's say, 1.5%, sorry. And we have been able also to obtain quite small full width at half maximum. Usually for quantum dash, you have something like 100 nanometers full width as FWHM. Here we have been able to obtain from 60 to 80 nanometers. And that means that we've been able to grow, I would say, quite uniform dashes in terms of shape and size. And on the right, you can see what we have been able to obtain on 3 inches wafers also. I would say that it's easier to have a good uniformity on 3 inches as compared to 3x2 inches, but still we are anyway quite happy with both of the substrate holders. And again, for AP layers that last only a couple of seconds, 3, 4, 5, 6, 7 seconds, it's quite impressive to observe the curvature change from one layer to the other. Maybe I will just end up by showing that from these studies we have been able to obtain quite good results in terms of lasers at 1.3 micron and also at 1.5 micron. And all this has been done at constant growth rates. And so practically, EasyCurve really helped us to optimize and be able to grow quite difficult structures in terms of epitaxy. I think that's pretty much everything I wanted to tell. Except that, yes, maybe, as I said at the beginning, that would have been great to have a tool that is able to measure the curvature on a multi-wafer position. That's my conclusion, I think. Yes. I'm done.